When it comes to using retro computers in 2026, there is one aspect of the entire experience that I find to be especially troublesome, and it's floppy disks and the drives that go with them. There are just so many potential issues with getting these things working that it can prove really difficult, especially for beginners, to get up and running. So I've had a number of videos on the channel where I've tried to troubleshoot drives and get them working again, with some success and some failures. But what I've always wondered is that there doesn't seem to be a modern tool out there to help you really troubleshoot these drives. So what I've gone ahead and done is come up with some new software that runs on the Greaseweazle, which is an excellent open source disk imaging system. And what this tool should allow you to do is more easily troubleshoot these drives and hopefully figure out what's wrong with it and get it working again. So in today's video, I want to show off this new software, and I even have a couple disk drives that I've set aside after testing a whole pile of them here that don't work. So maybe we can use the tool to get those working again. So without further ado, let's get right to it. Let's first talk about what the Greaseweazle is and what it isn't, at least out of the box. So what you see here is the Greaseweazle version 4. There are several revisions of this hardware. It doesn't really matter which one you have. I think they're all pretty much equivalent. And to put it at the most simple terms, this is a software-defined floppy drive controller. It's got a USB interface, so it plugs into a modern computer. This is the 34-pin interface that goes to your floppy drive via a floppy cable. And we have a microcontroller. And that's really it. The Greaseweazle project was created to offer an open source and inexpensive alternative to commercial disk archiving solutions that existed out there. So taking a floppy disk, putting it into a drive, and then reading the flux information, which is actually not the decoded data that's on the disk, but actually the magnetic flux transitions. The flux data can be saved directly into a file for later analysis and data recovery. You might be dealing with a disk that has an unknown format. Well, that magnetic flux or transition information can be read by the Greaseweazle and just saved onto your hard drive. It's a rather large file compared to, say, the capacity of a 5¼ floppy disk, but it allows for that preservation to happen later. So things like copy-protected disks or disks that are marginal, you can really try to recover as much data as possible by using this flux imaging capabilities of the Greaseweazle. What normally happens when you have a floppy drive controller IC on a disk controller, say on an ISA card and IBM PC, is that the flux information comes over the cable and it goes into the controller IC, and that decodes the data. For instance, say it's MFM encoded or FM encoding, and then that transfers it directly to the ISA bus. And that allows the software on the computer to not have to worry about the actual format of the disk, for instance, how the data is actually encoded. That's handled by the controller IC. And then all the operating system has to do is just read the data coming in, like a bunch of hex data. And if it wants to write to the disk, it's the same thing. It doesn't have to worry about all the timing, all the encoding. It just sends a command to the controller to say, I'm writing data. And then it sends a stream of hexadecimal data over the data bus to the controller IC. And it does that conversion back to the format that the disk uses. I think everyone knows at this point that a floppy disk can actually contain all different types of encoding. So FM, MFM, GCR, depending if you're using Apple II, Commodore, Atari, IBM PC, or any other system. And then the operating system itself lays down the sectors on here and how much data is in each sector and the format of the disk. But the actual base encoding is handled by the controller IC itself. And that's where the Greaseweazle comes in handy, because it is software defined. It's not bound by any one type of encoding structure. It just takes that flux information, loads it into the computer, and then the software on your much more powerful modern computer is able to decode that flux stream in real time. If you're, say, archiving an IBM PC format MFM disk, it can just decode that in software, save it as an IBM PC disk image, or FM, or Macintosh, or whatever format the disk is written in. The software is able to decode it because this thing just passes that flux information directly over the USB connector. Well, I can hear people asking, what does this device and all this disk archiving flux stuff have to do with maintaining a floppy drive on a modern computer? Well, where this comes in super handy is that because this is software defined, well, we can use software, or we can alter the software that drives this thing to do stuff to the disk drive that you might not otherwise normally be able to do. Let's quickly start by taking a look at the repository for the Greaseweazle project itself. And this is it here, floppy tools for accessing floppy drive at the raw flux level. Now, if you have a Greaseweazle and you haven't really used it yet, I totally recommend going through some of the wiki guides that are on the GitHub repo, and it talks about really how to use this thing to its fullest advantage. So it talks about reading images, writing images, talks about all the different formats that the Greaseweazle supports out of the box. And there are actually more things that it supports beyond this stuff, but this is just what the stock Greaseweazle software can do. But what's listed here is not the limit, because if you're just reading the flux data directly off the disk, as long as the drive can decode the encoding that's on there, like the electronics on the drive are compatible with it and can send a TTL signal over the floppy cable, then you could change the software to decode any other format as well. And I mentioned that the Greaseweazle is inexpensive, and it really is. Now, on the GitHub repo, you can purchase a Greaseweazle from one of these resellers, but it is open source. You can just make your own. And this is one of the official resellers. And you can see that the current 4.1 version, which looks like it is improved over mine because it has USB-C on it, is $40. Really reasonable. So now let's talk about trying to troubleshoot and repair disk drives, because that involves certain operations on the drive that are a little bit different than just normal disk archiving operations. And that's where, unfortunately, the Greaseweazle software, out of the box at least, doesn't really offer all the options that at least I would like to help me try to fix disk drives. And that's reasonable. That's because its design is really to create disk images off of physical media, or the other direction, make physical media from disk images. So it's not really designed for flaky disk drives where you might have mechanical issues or electronics problems that you need to troubleshoot. If you just try to, say, read an image off of a physical floppy disk from this drive and say this drive is not working, well, what ends up happening is it just times out because it gets an error. It can tell there's something wrong with the read process, and then you have to restart it. And if you're trying to probe around on a drive with an oscilloscope or exercise the mechanics on the drive by moving the head around and doing stuff like that, you need to be able to continually do that without things constantly timing out and giving you errors. So let's start off the demonstration by talking about what you're going to need to get up and running with the Greaseweazle, just in case you're not familiar. So obviously you need to have a Greaseweazle itself. My version 4 will suit us perfectly. You're going to need yourself a floppy cable, and I have this monstrosity that I've just been using for a long time. I don't know, it's got some tape on here. This is the end that you would plug into the Greaseweazle. This happens to have a plethora of different types of connectors on here. The edge connectors are going to be for things like 5¼ inch floppy drives, and then the IDC connector would be for most 3½ inch drives. This thing does have a twist in the cable, and this is for the IBM PC standard. The Greaseweazle supports both Shugart standard, where the actual drive select signal allows you to control up to 4 drives just on a straight through cable like this, but you do have to keep changing the jumper that's on the drive. Or you can use the twist and use the A and B drive convention. Of course, besides these things, you're going to need a floppy drive, so we'll be demonstrating with this 48 track per inch, aka 40 track 360K drive, so it's double-sided. This is standard Shugart interface. That's pretty much what the Greaseweazle, or at least this Greaseweazle, uses. Anything that has an edge connector or the normal 34-pin IDC, so Amiga drives, Atari ST drives, not Macintosh drives, but all the IBM PC drives and many other drives just use this standard 34-pin connector, and that is exactly what's compatible with this, at least when you just use a normal cable like this. This particular drive has the DS1 jumper set, so drive select 1 as opposed to drive select 0. That means I'll be using the twist in the cable, and I'll be telling the Greaseweazle we'll be accessing drive A, and I'm going to be sliding this on like so. The stripe on the cable always goes towards the notch if it's the edge connector. When it comes to connecting the ribbon cable to the Greaseweazle, you'll notice that my cable doesn't have the little notch here, which prevents you from putting it in the wrong way. So the way you know that the cable's in the right way is just look for these little kind of grooves in it, and that always is on the side with the notch. But another helper, at least on this connector, is it has a little triangle there, which indicates pin 1, which is always towards the stripe. And you'll notice there's also a little triangle on the floppy cable itself, so that just tells us that it goes in this way. Now we have to power up the disk drive, and while there is a power connector on here, I'm pretty sure this is only 5 volts, and this is only going to be good enough for hooking up to a 3½ inch floppy drive, and I wouldn't even recommend it because of course it's going to be powered up over USB. But I just don't really recommend it. You should power up the disk drive separately. And to do that, I'm just going to be using the bench power supply that I always use, which is just some kind of Pentium 4 era power supply. It's ATX, and I do have this thing on here, which allows me to plug it into AT motherboards, and it has a power switch on it. But you could use any kind of 5/12 volt power supply, that as long as it has a regular Molex connector, like so. This is what we're just going to plug into the floppy drive, and it's as easy as that. And of course, we got to plug the USB cable into the Greaseweazle. This should just show up as a COM port on my Windows 11 computer. And here we are in Device Manager, and this particular device shows up as COM 12, although it doesn't really matter because the Greaseweazle software will auto-detect and find the device. You'll notice I have COM 13, which is currently disabled. That's another Greaseweazle that's permanently installed inside of my lab computer. And in order to make this demonstration easier, I don't have to like manually select which Greaseweazle I'm going to use. It's just easier just to right click and disable the one I'm not using when I'm using this external one on the bench. Now, the one thing about Greaseweazle is that it is command line based. It doesn't have a GUI. Now, there may be front ends out there that I haven't tried because I just use the command line because it's easy enough. Here in the Greaseweazle directory, if I just type GW, this is the main application. And the help in here is pretty decent, although what I have done is I've created a bunch of batch files and scripts for myself that allow me just to drag and drop a particular drive image. And inside the batch file already has the whole command line all, well, set up properly for that particular format. So if I need to make like an IBM PC disk, I can just drag the disk image onto the batch. It just runs the Greaseweazle command line application, passes it the name of the image, and then creates the image. It's all pretty easy stuff. Well, if you try to write a disk image, right now it just says, you know, you need the arguments, but you can type GW-write-H, and then this will give you a little bit more information about all the different formats and stuff and other command line parameters that you can pass it. These are all the formats that the current version of this Greaseweazle tool supports, and I've downloaded like the latest release that's on my computer right now, so this is pretty much everything that's on here. Now let's do a few operations on this disk drive. So the first thing I'm going to do is find the power switch, which is right here. Nope, it's not going to work until I plug in the power supply. There it is, drive is now powered up. I'm going to put this disk in here. So it's spinning, so I know the drive is working. Now, if we take a look at the Greaseweazle commands, we can see there's like info, which just tells us, hey, we're using Greaseweazle v4 on COM12. We can type the command Greaseweazle RPM, and it will spin the drive, and it will report back the RPM, which happens to be 300.101 RPM. And that is using the index sensor that's on the drive, because if I take the disk out and we try to run this again, I think it will eventually time out. Yeah, no index. There's the Greaseweazle command seek, so it allows you to seek to any specific track. Let's just go to 20. 20, okay, there we go. It basically recalibrated the drive back to 0 and then seek to track 20. This is a very noisy disk drive, but it does work. It's just noisy. And there's another command called clean, which is really for inserting cleaning disks into the drive. And what this does is it makes the head move around in a cycle, a zigzag cycle. Now, if we're going to run this, we have to specify that this is only a 40-track drive. Otherwise, it's going to try to seek all the way to track 80, which is going to hit the head into the bump stop. So we'll do cylinders 40. You can see the zigzag motion this thing is going in. Now, I've used this cleaning routine to actually exercise the head assembly after I've cleaned and lubricated it, because you can alter the number of passes and have it run many, many times. So it spins up the disk and it just keeps moving the heads around. I don't think you actually even need to have the disk in there for this to work. Let's just give that a quick try. Yeah, it works even without the disk in there. So you can run that command without potentially damaging your disk or something like that. But that's actually about it for all the commands that Greaseweazle can do. I mean, other than like reading or writing a disk. So let's try reading out this disk that's in the drive here to, well, I'll do it as raw 250 and I'll save it to my D drive. I think I have this right. Cryoflex image. There we go. This drive is so loud. Right, so here goes reading out the disk. You can see it's like heads are moving. And I mean, I could take the disk out here and look what happened. It kind of aborted because it's not finding the index sensor signal from the hole that's in the drive. So it doesn't keep sitting there spinning, it just aborts out. So these are the kinds of things that kind of annoy me about the built-in tools. If I'm going to be trying to troubleshoot a drive, I don't want it to be continually, reading different tracks like it's doing now and checking to make sure that the index sensor is working. I just want it to keep going. Right, so those are the basics. We need to be able to talk to the disk drive with the Greaseweazle, with the stock Greaseweazle software, before trying to use my new tool to troubleshoot the drive. So my utility is called GW-DIAG, and it exists in the Greaseweazle directory because this is actually not brand new software. I'm just using the Greaseweazle Python scripts and libraries that are already there in a way that the stock Greaseweazle software doesn't do. So when we run this, we can see the parameters that this tool can take. Really, the only thing that really matters is the rate one. We got to tell it the kilobits per second that we're going to be reading the disk at. So we can type like 250 kilobits per second, hit enter. And what this will do is it will start up, the loud drive will do its thing. And what it's doing is it's just continually reading the same track over and over and over again and decoding it and giving you a bunch of helpful information. So of course, starting on the left, we have drive A, because that's what we're using. We have the current RPM of the drive, so I can slow it down here by putting my finger on it, or I can just take the disk out altogether and it says RPM error because it's not actually reading any RPM off the drive. But of course it doesn't stop, and that's the important thing. It will keep going even if the RPM signal doesn't really make sense. Next thing is the data rate, so 250 kilobits per second. That is typical for a double density disk, which is what this is. 500 kilobits per second would be a high density disk. And then of course there is 1 megabit a second, which I think is like those 2.88 meg drives, which I've never actually seen. The current track we're reading is track 0. We're on head 0, so we're on the bottom head. Head 1 is the one on the top side. We are currently reading 9 sectors out of 9. So this particular format, which this tool is designed to read IBM PC, like MS-DOS formatted disks, and those, when you're using a double density disk like this, have 9 sectors. So sectors is 9 out of 9. The next thing that says OT no is off track. I'll get to that in a second. The next signal we have, and I'll just stop it so I can highlight things, is the write protect signal. So it's currently high, and it means the disk is unprotected. So that actually gives you information on whether the write protect sensor is working and the signaling that goes from the drive to your computer. So it's going to the Greaseweazle. It's just telling us that pin 8 is currently high. Now here's an example. Let's start this up again, and we'll see that it says high, but if we take the disk out, notice it says low protected, and that's because since I slid the drive or the disk out, the little notch, well, it ended up hitting the solid part. So currently with the drive or the disk not in there, it says unprotected. But as soon as I start to slide it in, now it says protected. And that's because the beam is being broken by the disk itself. Next thing is the disk change signal. Now I found this doesn't really work properly. I think it's actually this Greaseweazle or whatever, so I left it in there, but it is pin 34 high. It's pretty much always high. I've never seen it actually change. Maybe in some situations it might, but at least I guess with this floppy drive, that signal is just always at 5 volts. The next thing is the track 0 sensor. Now that is low because we're actually at track 0. See, it says track 0, but if we hit plus, we go to track 1, and now that track 0 sensor switched from low to high. So this right here can help you troubleshoot whether the track 0 sensor is working properly. And let me tell you, if it's not working properly, like say it's out of adjustment, it's this thing right here, that'll cause the disk drive to have all sorts of random issues. The next signal is actually an output signal. It comes from the Greaseweazle to the disk drive. It's pin 2. It's the density select signal, but sometimes it's the track or TG43. That's for 8-inch disk drives. In this case, it doesn't really matter what this signal is. Now it's currently low, but if I push the D key, it switches it to high because it's an output coming from the Greaseweazle to the drive. This drive doesn't use it, but some disk drives do. I'll demonstrate with another floppy drive what that density signal can do depending on how the drive is configured. So going back to the OT or the off-track indicator. So currently we are reading 9 sectors out of 9, so the correct amount. But say there was a problem with the pressure on the head. So I'm going to lightly lift up the head off the disk. It should stop it from reading, I think. Yep, see, we're having all sorts of issues now. And notice how it says S0 of 9. So it actually was unable to read sectors off the disk anymore. But you might be having issues where like the heads are dirty or the alignment is off and you're not going to get an accurate read. In fact, there are a couple 8s appearing there. Now the reason why the 8s are appearing is because this floppy disk, I made this disk in a 96 track per inch drive, basically an 80 track drive, that's 80 tracks. This is a 40 track drive or 48 track per inch. That means the heads on this drive, the track width that it reads and writes to the disk is wider than an 80 track drive. And if you've ever heard people talk about if you make a double density disk in a high density drive, it doesn't really always work properly in double density drives. That's why, because the tracks that it lays down onto the magnetic media are much thinner than this drive expects. So occasionally you can have reading problems, but you can especially have issues when you write. Because if we write new sectors onto this disk, we're going to be writing with wider tracks mixed with thinner tracks from the 80 track drive. It's just not ideal. Ultimately, if you're going to be making disks that are going to be used on a 48 track per inch drive, so that would be like an Apple II, for instance, Commodore 1541, you should really be using a 40 track drive, a 360K drive, which is what this is. Anyhow, back to this. It's just sitting here spinning away. It looks like most of our reads are good. I saw an 8 up there kind of go by. There's another 8. So it's missing the odd sector. So it's kind of telling you that things aren't really perfect. Now, this drive works fine. It's just this disk, because it was written in the other drive, that's where the issue is. Now, here's where the off-track thing comes in really handy. Imagine I move this head manually. Okay, actually, this has a jack screw for moving the head, so I can't just physically move it. Oops, I stopped it from spinning there. So I need to move the heads manually. So you can use the plus and minus key to move one track at a time. So see, we're up on track 4, track 3, but I can also just jump to like track 30 by pushing the 3 key. Now what I can do is I can reach in here and move this jack screw manually. Okay, there we go. So our sector track, our 9 of 9 disappeared. See, it went down to 4 and then it went to 0. But what happened is off track suddenly appeared. Now what this is telling us is that the drive, or the controller, thinks it's on track 30, which happens to be the Greaseweazle, but this would be no different than if you had like an IBM PC. But the sectors themselves that the drive was reading were actually from track 28 and track 29. And ultimately, I think that was because I was moving it, and then it settled on reading track 28. So it was reading 9 sectors correctly, but those sectors were sectors that were coming from track 28. Now, this is all possible because with this format, IBM PC format, each set of sectors actually has an encoded track value in it. So that way, when the drive reads that sector, it goes, oh, hey, these sectors, these are actually track 28 sectors, and I'm on track 30. So something's wrong mechanically with the drive. Now, that particular off-track fault can happen for a number of reasons. You could have alignment problems on the actual stepper motor. The stepper motor can be failing, but the most likely thing that's happening is that the stepper motor and or the tracks where the head moves are gummed up, from age or whatever. So when the disk controller or the Greaseweazle in this case try to move the heads to a particular track, it doesn't land on the correct track and you start reading the wrong tracks, which of course, if you're on an IBM PC and MS-DOS or pretty much any computer, that's really going to freak it out and it's going to start giving you a bunch of errors like sector, address errors, and things like that. Now imagine you had an alignment problem and the head was actually reading between 2 tracks. Then you could end up by seeing a whole bunch of this stuff where you have OTs and you're seeing sectors from 2 adjacent tracks. It would really never happen where you'd see like T28 and then T15, not in a steady state. But if you keep seeing this over and over again, that's really an indicator that you either have an alignment problem on the drive you're currently testing, but you also could have an alignment problem on the drive that made the disk. And that right there is one of the big caveats of a test like this that I'm demonstrating. You need to have a disk that was made on a known good drive. So either a commercial disk that's not damaged and not moldy or failed, or a disk that you made or someone made for you in another drive that is known good. Like it can read its own disks, it can read disks from other drives, because that's one of the problems. If you have a misaligned drive and you make a disk, well, that same drive can read its own disks, but if you take that disk and put it in a different drive or other drives, it won't be able to read those properly. So that is the one extra thing you're going to need to do this testing. Besides the Greaseweazle, the cable, the power supply, and the floppy drive, you're going to need a good disk that was written in another computer that had good alignment, and that drive is known good, and the disk is known good, and really it should be an IBM PC MFM format. Luckily, IBM PCs are very plentiful. You go to any kind of show, or if you know anyone who's into retro, there's probably someone who has an IBM PC that has a working floppy drive. So it needs to be a 40-track 360K drive in the case of this test that we're doing here. Or if you're testing a high-density drive or you're testing a 3.5-inch drive, you need to get the similar media made for those. Even if you're testing something like an Amiga floppy drive or an Atari ST floppy drive, you need to be using a double-density 720K 3.5-inch floppy disk that was made on a PC. And the reason why I picked the IBM PC for the disk format that this thing uses is just because it's the lowest common denominator. There's so many IBM PCs around that you can, ask someone to make a disk for you. And then B, the sector format is such that it also allows you to be able to see when it's off track. Now let's restart this test process. Oh, this drive is so loud. I get so shocked by it. Okay, so I'm at track 30 right now. There it is, T30. Now I can push the H key to look at the other head. So now we're reading the top of the disk. Now the problem is with the IBM PC format is it doesn't indicate on the sectors whether you're reading head 0 or head 1. So if there's a problem on your drive where it's not able to correctly select if it's head 0 or head 1, you could be fooled by that. And I have had disk drives before where there was something wrong with the head selection logic and it was always reading the bottom head 0. It always looked like it was working. You could image the disk and you'd see everything, but that was specifically because you were just always reading head 0 or the bottom side of the disk every single time. There's really no easy way around that particular problem other than maybe taking your floppy disk, bulk erasing it, and then taking it to someone's good disk drive, whether yours or someone else's, and writing a single-sided MFM image onto it. So it's only on side 0, on the bottom side. That way, when you do select head 1, it's not going to be able to read any more sectors anymore. In fact, let me demonstrate that. Okay, so I've gone ahead and I degaussed this disk, so I have a bulk eraser for tapes. Let's put it in the drive, see if it can read anything. No. So we have RPM, but see sectors is 0 of 9. And we change to head 0, same thing. Let's go to track 0. Same thing. It's not reading anything on any of the sectors. Okay, perfect. So this drive now has a single-sided image on it, and it was also written in a 48 track branch drive. So we shouldn't see those S8s anymore. Yeah, it looks good. Now, if I push H for head, well, that didn't work. We are on side 1 on the top side, and now there are sectors being read. Oh, just on track 0? Oh, it's a little bit of a bug. Okay, well, I guess I'm going to need to investigate that, because obviously we're back on track 0 and there are no more sectors. So it seems that we have a little bit of a bug. Let's start this again. This is it. It says right here, 0.1 test pre-release. Right, head 0, sectors 9, and just switch to head 1. Okay, well, it still says 9 of 9, and hit plus to go to the next track, 0, 0, and we go back, 0, 0, and let's change back to head 0. Okay, so that's like, it doesn't change the heads when you actually hit the H key until you actually seek the head. All right, I'll investigate that. And there's one extra command you do have, and this is in case you're having trouble with the stepper assembly and it like gets off track. So right now we're on track, but if I just turn the jack screw, there we go, now we're off track. Now what you can do, and if you just hit plus and minus, this doesn't really work because of course we're changing the tracks. Notice it got 30, 29, 28, but we're still off track. Now the off track is moving in the same amount, but to get us back on track, you know, pun intended, you hit the R key for recalibrate. And what it does is it should reseek, and now we're back on track. So we went back to the track that it thought we were on, 29, and now we're getting 9 of 9, so we're no longer off track. Okay, so this drive, which is a 1.2 megabyte TIAG FD55GFR, this is a dual speed drive. Now, normally it's not in dual speed mode, but I think I wrote jumper I sets it into dual speed mode. Now that particular jumper to switch the dual speed mode, that's gonna vary from one drive to another. And I gotta tell you, it's not always easy to find the service information for the drives to switch that mode. Okay, so because this is a dual speed drive, the density select output that you can change with the D key actually affects the RPM. So currently it's running at a nice exact 300 RPM. We are reading this drive perfectly, or the disk perfectly rather, S9 of 9, and we hit the D key and it gets an error line. That's just the Greaseweazle, I think. And then it shows us 360 RPM. Now at 360 RPM, of course, our sector decoding is not working anymore, and that's because our data rate is wrong. We're currently at 250 kilobits per second, but the drive is spinning too quickly. This would need to be 300 kilobits per second for it to even try to read these sectors, which I think we can actually do. So let's try 300. I haven't actually tested this before, but that should be one of the valid rates. Okay, so currently it's not able to read because it's at 300 RPM. It defaults to the density select of low. But if we hit the D key, not quite there. This is some stuff I probably need to troubleshoot, and that's because mainly I'm always trying to fix 250 kilobit per second drives or 500 kilobits per second drives. This whole 300 kilobits per second is a really weird data rate that IBM came up with when they made the 1.2 meg drive standard that is super non-standard, because pretty much everything up until that point had always used 500 or 250 kilobits per second, at least with the MFM or the FM standard that are used on 8-inch, 5.5 or 5.25 inch and 3.5 inch discs. So there are some other parameters so you can pass this GW-DIAG, like the device name. So this is like for the COM port of your particular Greaseweazle, the drive ID. So it just defaults to drive A, which is what's using here, but of course A or B, and we have 0 to 3 for the Shugart style. The number of cylinders that the drive actually has, so you can't try to seek past the limit. You could specify the encoding type. So if you do want to tech with a disk that's FM encoded, like on an 8-inch disk drive, that's more common there, you can do that. And then you can also generate the TG43 signal. So that's using that density select signal. Instead of it going out and trying to select the spindle speed, it adjusts the precompensation that the drive uses for reading the disk. And it explains it here. For an 8-inch drive, it is high below 60, and then it's low for a 60 and above. Typically, 8-inch drives, I forgot, they're like 70-something tracks. Typically, they're not a full 80. And the reason for this precompensation thing is because the disk is so big, it's physically spinning so fast on the outer edge of the disk versus the inner edge that the read and write strategy for the disk drive usually has to change. Some drives have it built in automatically, you don't need that signal, but most drives do need that signal. So this can generate that signal. And then this just explains the output that we've already gone through, and that's pretty much it. There's not much to it. It's just I wanted a tool that could just run continually and not error out if the RPM signal disappears or some other signal seems wrong. Just keep giving me data and allow me to probe around on the drive. Even if I unplug the drive, plug it back in, unplug parts of the drive, this thing will just never stop running. And that is exactly what I needed. It feels like every other tool I've ever found that allows you to do anything like this always stops as soon as there's a weird thing coming into it. Even IMD, Image Disk for MS-DOS, that was the tool I used to use the most for this purpose before. But even that just aborts as soon as the RPM signal is no longer seen. So if you take the disk out or it stops spinning, then that process stops and you have to kind of cancel out of it and then go back into the align disk thing. The one thing the image disk does that this doesn't do is it generates a tone to tell you if it's on track or off track. It does pretty much everything else except for that aborting if the RPM goes away, but that tone can be useful. So you can adjust the drive without looking at the screen. On the other hand, though, I find that a beeping on image disk really annoying and I usually just shut it off. So that's why I didn't even bother to implement it with this tool. So the last thing is, how do you get this tool? Well, it's on my GitHub, and all I did is I forked the Greaseweazle repo, and then there's a new branch here called DIAG, and I've added a README to talk about what this thing does, which is pretty much everything I've just showed you. There's a screenshot of it there working, all the relevant output things, and the usage. And then in the getting started section, it talks about what you need to do to get this running on your computer. And all you really have to do is just clone the GitHub repo down to your computer and then just run the batch file, and it will basically do everything else for you. And all you have to do is just download zip right here if you don't have Git installed on your computer, which is what I was mentioning right here, this Git command, clone, and you just run the batch file and that'll take care of everything else. There's some Python libraries you're gonna need. You will need Python 3.8 or newer in your path. So you should be able to just type Python 3 in your command prompt. And if that works, then you're good to go. Now, I will have to mention, and people probably see this here, is that this does not work on Mac and Linux right now. And the reason why is on Windows, you don't have to compile anything to make this work. There's already these little compiled bits that come with the Greaseweazle executable that allow these Python scripts to just work. But on Mac and Linux, apparently you have to do some compiling. Although I'm not sure about that fully. It goes without saying that Greaseweazle is fully open source. So if anyone else wants to kind of implement this stuff better than I did and make it work on Mac and Linux, absolutely please be my guest. You can either create a separate fork and then add the Mac and Linux support over there, or if you want to do a pull request and I can merge it back into this one, I'm fine with that as well. Ultimately, what would be the most amazing to me is if this functionality, this diagnostic functionality, could just be merged into the source Greaseweazle release. That way it would just work for everyone and you wouldn't have to download anything special like this. But the way it would work right now is you download the original Greaseweazle release, put that on your computer, then you download or clone this repo and stick all those files into the same directory where the Greaseweazle release is. And then you'll have access to the Greaseweazle command itself and then the GW-DIAG command as well. That stuff will all work and coexist together. Let's start by trying to troubleshoot a floppy drive. This is a JU-475 from Panasonic that is not working correctly. I find these drives to be generally pretty reliable. One thing that's kind of funny, DS 1 through 4 as opposed to 0 through 3. So DS 2 on this drive is the correct way to do it if you have a twist. This is a 1.2 megabyte drive, therefore it's almost certainly going to be running at 360 RPM since I've never touched this drive to try to switch it into dual speed mode. So I have a few shortcuts for the diag script just to run it in the different modes, and let's try running it 300 kilobits, and we'll be using double step, a new feature that I've added since I just recorded the last segment. I also added the 300 kilobit per second fix, and that means it automatically guesses the correct number of sectors. And of course, that's what I ran right here. So you'll see it when I stick in the floppy drive. Oh, the motor sounds like it's going way too fast. 876 RPM on a 5¼ inch disk drive. Well, that's not right. It started at 900, actually came down a little bit. You may also notice that I added color coding. So it's red if it's not reading anything but the correct number of sectors. Obviously, we have a problem with this drive running at warp speed. Wow. You might be able to make it out. The spindle is just going so fast. Let's see if we could slow it down. Oh, look, it's reading the sectors. If I slow it down with my finger. Sorry, you didn't see that, but yeah, it was actually reading the sectors correctly. Okay, well, from a problem perspective, the issue is going to lie on this board, without a doubt. There's the speed controller right here. It's this IC package. And unfortunately, we can't get to any of this because it's all underneath the spindle motor. I'll try popping this off, but I'm not sure I'm going to be able to fix this in this video. Now, sometimes there's going to be some bad caps on this little board, and maybe that's our only problem. The way this is hooked up to the main board is there's going to be power going into this, ground, then there's going to be a signal that turns on the motor and another signal that selects which speed to select. Because almost certainly this does support dual speed, it's just not configured to do that with the jumpers on here. There's actually 5 wires that go to this, and I just rattled off 4, so I don't know what the extra one is unless it's 5 volts, so there might be 12 volts and 5 volts, depending on how the logic is on here. And then the motor on signal, and then the speed control signal. So that would be all 5 of these wires, which are connected right there. Now, sometimes these little screws are Loctited on, although this seems like it's not. So that's good. So I can actually get these off. I've had to cut slots into these screws before because I accidentally stripped them out, but I did not strip these. So this is a brushless DC motor. That means this thing has the magnets in it, and there's going to be a bunch of coils on the PCB underneath. So you just need to use a tool to kind of lift this off. And since it's magnetic, it's stuck on there. There it is. There's our permanent magnets. All right, 4 fasteners on the PCB. Should lift off. What is this stuck on? I can just see down there. You can see the coils. There's some extra wires. What are those connected to anyways? I decided to spend like the extra couple seconds just to get this little board off because I think this is the speed controller cabling right here. And that means I can fold this down so we can look at it. Ah, now I see what's going on. These 2 wires go to the LED for the index sensor. That's what that is. All right, so the question is, why is this thing running too fast? I unfortunately suspect that it's the speed controller IC. These Hitachi chips are used on all sorts of disk drives, and I've had these fail a number of times. Now, incidentally, one thing that confirms my suspicion is the cabling that comes from the main controller: ground, 12 volts, 5 volts, SS and MS. I bet MS is motor signal, so that's motor on and off, and SS is the speed signal. So that would be the 300 RPM or the 360 RPM mode. And that little chip is what's handling both of those. There'll be a signal that just goes from there directly into that chip. And you can see these little black sensors. There's one there, there, and there. Those are the Hall effect sensors that can sense the magnetic field from this permanent magnet. And that allows this chip to know exactly the speed that that is spinning at. So there's no speed adjustment on here because the chip itself is what regulates the speed. And the problematic part here is that because the chip itself is doing the speed regulation, there's no one component on here that could say fail, one of these passives, for instance, that could then cause the speed to run out of control. You can tell by the fact that there are 6 coils here that this is a 3-phase AC induction motor. I think that's the right term for it. Essentially, it's a brushless motor that has waveforms that come out of this chip that go through these coils and they rotate around. So there'll be 2 energized at any one time, and they just rotates very quickly. And the chip knows the position of this spinning disc based on these Hall effect sensors. So as the disc spins, it rotates the magnetic field faster and faster and faster until it gets to the correct speed, 300 or 360 RPM, and then doesn't go any faster. And it regulates it just perfectly. And if you load up the motor by, say, inserting a diskette, it still is able to maintain that speed perfectly. And this seems to have lost its ability to regulate speed, but at the same time, it obviously has an ability to rotate those magnetic fields around through these coils to get the motor spinning. That's working. It's just the speed regulation is broken. So the Hall effect sensors, which obviously work because it's rotating the magnetic field properly, they're working, but yet why is the chip no longer regulating speed anymore? Here's our data sheet for the HA13456, funny part number. It's a 3-phase brushless DC motor driver, and it can provide 1 amp per phase, intended as a floppy drive spindle motor driver. It has the Hall amplifier matrix, control amplifier, current control, FG amplifier 0 cross detector, oscillator circuit, high-speed discriminator, 300 and 360 RPM operation, integrating amplifier. It pretty much just sort of does it all in one. So we can see the 3 Hall effect sensors. We can see the output amplifiers, which is going to be going to the coils. Looks like this pin is responsible for starting and stopping the motor. So high is a stop, low is a start. That does work because it obviously stops when I take the disc out, only spins when I put the drive in there, or the disc in there, I mean. And this is really the issue where I'm concerned. So there is a crystal oscillator. Maybe that's bad. I should at least check that, right? And there's our mode select. So actually MS is the speed select, and then we have speed discriminator. On the output of the speed control, there are some passives that go into the integrating amplifier circuit and the buffer and this, that, and the other thing. and then that allows it to select which speed it's running at. So I think I'm going to spend a moment just to poke around with my multimeter just to see if like these caps are good. I'm sure they're fine. And these passives, like the resistors and everything, are there. These little caps, those never fail. But ultimately, I fully believe that it's the speed controller that's probably dead. And unfortunately, it seems like everything is in perfect shape. All those electrolytic caps are fine. All the passives are completely fine as well. I really don't see any issues. There's no visible corrosion on this board. There's no broken traces. The soldering is good. There's no cracks in it. Yeah, unfortunately, I think the speed controller itself is our problem. Incidentally, with that cover removed, I didn't mention this before, but there's a little adjustable pot here. You might be tempted to turn that to try to adjust the RPM, but do not do that. As we have just shown, the speed control entirely happens on that bottom board. It has nothing to do with up here. This is probably something to do with the differential amplifier for the read-write heads, so I would not touch that unless you are ready to scope all the signals on here and try to get this thing all back into calibration again. What I did notice is there's a BX jumper location, and usually on these Panasonic drives, BX has to do with dual speed operation. So the BX jumper is right there. So let's give that a try and see if that changes anything when it comes to the speed, because maybe this thing works in 300 RPM mode. It would have definitely been set to only operate in 360 RPM mode the way this was out of the box. Let's pop this in. I'll know right away. No, it's still like, the motor's like spun way up. Oh, and I just noticed the whole time this was actually running. That's funny. So we are in low speed now, and changing the density select line does absolutely nothing. So I'm pushing the D key, and this should be changing between high speed and low speed, and that is just not happening. Well, not all is lost. I definitely come across broken 1.2 megabyte floppy drives from time to time, and I wouldn't be surprised if a lot of drives use this exact same IC. So next time I find a damaged, broken drive, I'm going to check to see if it has that IC on it, and then maybe I can bring this thing back to life. Next drive to look at is this. Now this mint condition, pristine looking drive is actually a Shugart SA400L. I don't know what the L means, but the SA400 was the very first 5¼ inch floppy drive. All the other 5¼ inch floppy drives were really modeled after this and really cloned this thing. I'm sure lots of people have heard the story about Steve Wozniak making the Disk 2 floppy drive system for the Apple II, and Steve wanted to make it really cheap compared to, well, the price of floppy drive systems for other things. So apparently Steve reached out to Shugart and said, hey, send me some of your mechanisms. I'd like to test them out, and I don't need this top board, which apparently was kind of one of the more expensive parts. And the story is that Shugart sent some of these mechanisms, and they were called, I think, the SA390s, because they were missing that. They were also missing the index sensor. And apparently they were marginal drive mechanisms. I don't know what that really means, or if it's true. But apparently Steve's analog board and the Disk 2 interface system was so good, it even made the marginal mechanisms work. Either way, the SA400 is the Shugart mechanism that originated the interface standard, the 34-pin standard that all these other drives use. So that's kind of cool. I didn't realize that this was one of them. So my note on here says 180K single side, because of course that's what the first ones were. 48 track per inch, we know that. Not seeking, no track 0, I probably meant by what I wrote there. This thing is in incredibly clean condition. It's not like it's perfect, but it seems like there is just no dust on this thing. Spins well. The belt looks fine. I mean, it's all shiny metal. I mean, this is in great shape. Let's plug it in and see exactly what it's doing. All right, so right off the bat, one thing I'm noticing is that I think this is the drive select. So we have 1, 2, and 3. Well, if we're gonna use the twist in the cable, it needs to be set to, well, drive select 2, and we can see that that's broken. So I can either take this thing out and just put a jumper in this HL position and then put one in there, or I can switch this over to the straight through section, and we're gonna change this to respond to drive select 0 instead of using A and B. All right, so I'm editing the batch file. So GW-DIAG.bat, rate 250, drive 0. Slide in our test disk, which happens to be 180 kilobyte disk anyway, so single-sided, which is exactly what this is. Well, it's running. Okay, so speed's a little slow. It's very noisy, but I have a feeling that's this clamp on the top. That's so loud. Yeah, I think it is that. But it's also not reading any sectors. The drive LED or the drive activity light is on. Can I seek? Oh, yeah, you can seek. No, we're not able to seek because it went back to track 0. So that error that popped up here is because I went to track 0, 1, and then basically ended up back with the track 0 signal on. So see how it was low, then it went to high, so it like moved a little bit, and then went back to low. All right, so what we have to do is to gain access to like the mechanism underneath, we got to take these screws out, and they are tight. Guess this drive is old. What's the date codes on these chips? This one says 82. 82. Okay, so this is a 1982 drive. So this is a very late model drive. Now I realize that the L in 400 in the model number is that they integrated the speed controller, this little section, onto the PCB. And in older drives, it's a separate board mounted to the back of the drive. So this is like a cost-reduced one. This mechanism came out in the 70s. Don't remember exactly what year it was, but it was definitely like 75, 76, something like that. All right, so to get this off, we just slide this like so. And now we can kind of expose everything. I'm just going to move this metal piece out of the way since the drive is currently powered up. This will give us a view of the stepper assembly to see like what's going on. So yes, it is like a turntable stepper. It has a groove on it, and as it turns, it moves the entire head assembly. The program is still running. What happens if I try to seek right now? The motor is turned off. Okay, so I'm pushing plus and minus. We can see it kind of like moves it back and forth. As far as reading the disc or not reading the disc, the heads look perfect, perfectly clean. Obviously, I can't put a disc in there and have it work because the heads are unplugged currently. Now, one thing about the stepper is it's currently energized, and that pretty much locks it in place. Now, if I turn off the power to the drive, which is right there, oh yeah, now I can turn this very freely. So definitely the windings inside the motor are energized, and there's also no friction in turning this at all. It's moving very nicely. As far as track 0 itself, which I'm pretty sure works, see this micro switch right there, the little blue thing? That actually gets pushed if we move the head into the 0 position. Will make its way there eventually. There it was, click. Actually, that kind of makes me want to try to read the disc. If I just manually put the stepper into the track 0 position, can it actually read any sectors off this thing? Oh yeah, look at that, we're reading sectors. So when I manually move the heads into the 0 position, now we're getting a good read. I mean, the RPM is too low. This will be the speed control because that's the speed controller. That I can adjust. I mean, it's fine, obviously. 295 is okay. There's some goop on here. Gotta break that off. 300 RPM, looks good. Now the noise we're hearing, it's kind of hard to get this off. There we go. The noise we're hearing is this. So if I put my finger on it, it's quieter now. It's that spindle bearing. I've never really found a good solution for quieting these spindle bearings. Putting oil on there doesn't really seem to work. I think you have to really take the little C-clip out and then add a little bit of lubricant and do stuff. And then it will quiet down a little bit. But you can't put too much oil because it will drip onto the disc and really kind of screw things up. Oh, it actually worked. Track 1 is reading. Wait. This is working now. I don't believe it. We know it's real because the sectors would be red if it was reading the wrong track. It would be off track, and it's not off track. How did this just start working all of a sudden? I just moved the stepper all the way to the 0 position. Let's recalibrate. Now it's not working. Okay, I think what's going on now is that I gotta stop this because it's just causing the stepper motor to vibrate very quickly left and right. I think what's happening here is that these old SA400s, they actually don't work generally very well hooked up to a modern computer. And by modern, I mean stuff from the 80s. And that's because the turntable stepper assembly, it has a lot of mass. Therefore, if your stepping commands are too quick, it actually causes it to not work. So if you're trying to go from like track 10 to 0, recalibrate, and you issue the step commands really, really quickly, it just doesn't really work because there's a lot of mass turning that thing. You got to go more slowly. You got to be more directed with your step signals. Now with computers like the Apple II, which use this mechanism, obviously the SA390 version of it, they step pretty slowly. But later versions of MS-DOS, and I think the Greaseweazle, it just does it pretty quickly. And that's probably something I need to add to the diagnostic tool to change the step rate to slow it down. And the built-in Greaseweazle utilities does actually support adjusting the step delay. So it's 1,000 microseconds right now. So I changed it to 20,000. So I tried to use the clean command. That still didn't work because basically what it does immediately is it goes from track 0 to 9 back to 0, and it's looking for that track 0 thing and it never hit. So that therefore it wasn't stepping properly. So it suggests 20,000. Well, we tried that. So I switched it up to 30,000. See if that makes a difference. That did. It's working now. Oh, well, now it's hitting the end stop. That's also my bad. I think we got to do cylinders. I think 35 is the maximum. Okay, there we go. Yeah, these old mechanisms, I don't think they even support 40 tracks. I think it's less. So we don't even need the disc or the head hooked up, so we can look at the seek speed with this 30,000. There it goes. Yeah, unfortunately, these are just slow mechanisms, and computers designed to use these will step slowly, so they'll be fine. But the more modern, faster step speeds, they just are too quick. I've switched it back to 20,000. Let's look at how that looks. See, it was kind of working. I almost feel like maybe 25,000 might work. Okay, so this is, what are we looking at here? This is 25,000. Looks like it's working fine. You also notice this has a solenoid to actually load and unload the head. So it lifts the little pressure pad that allows the disc to keep spinning without actually wearing the disc down. And the reason why they do that is because these older systems, if you're using 4 drives, the motor select is shared across all the drives. So the motor will be on anytime any drive is being accessed. So if you have a lot of access happening across the drives, all of these will be spinning. But only when the drive's selected does it actually engage the head by lowering this solenoid. So if I turn this back on, you hear it click. And there it goes. And this is being noisy. So 25,000 for the step time is about all this thing can do. And I think 10,000 is the default. And even with this set to 25,000, I am quite sure that this does not work and this overrides that. So we can tell if I try to go to like track 30, yeah, goes way too quickly. Yeah, I can just sort of see this trying to move. So this drive actually works perfectly. The only thing that's wrong with it, I was trying to step the head too quickly and, well, the noisy clamp, but that's a separate problem. So what this tells me though is I need to add an extra feature to the GW-DIAG that allows you to control the step rate, because obviously it's just overriding the delay value that you set at the command line for the Greaseweazle. So yeah, I'll just add an optional parameter to allow you to set it to anything like 25,000 like this one, and then I'd be able to properly test this drive as well. And with all that said, that's going to be it for this video. If you have any ideas of new features that I should add to this that will improve it even further, then comment down below. And I know there's going to be much smarter people out there who are going to be able to make this work on other platforms or make this into a GUI or who knows, do all sorts of cool things with this. But I know for me, I will be using this anytime I'm troubleshooting a disk drive because it's right here, it's on my lab computer, and I always have this extra Greaseweazle handy and ready to go for plugging in for exactly purposes like this. And now I don't have to bust out an old IBM PC to do diagnostics on disk drives, which was fine, it worked. It's just IMD has some things that really annoy me about it, and this is so much easier. I just double click a little batch file and it's up and running. It's so quick and easy, and it kind of does exactly what I want. So there we go. If you like this video, thumbs up. If you didn't, you know exactly what to do. Huge thanks to my supporters, huge thanks to my subscribers, and I mean, all the other YouTube junk, and I guess that's gonna be that. So stay healthy, stay safe, and I'll see you next time. Bye.